Okay, so we're given some handy-dandy theorems here. As we've been talking about, theorem 11.1.1 says that if a line is tangent to a circle, then it is perpendicular to the radius drawn from the point of tangency. Similarly, down here, if a line is perpendicular to a radius of a circle, then it is the tangent line to the circle. So the prompts that I've been giving y'all asking about the relationship between the radius and tangent lines, they are perpendicular to each other. So wherever you draw the tangent line, it must be perpendicular to wherever that radius would be drawn. So let's see how we can use this information to actually do some math. So first example here, early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. What was the distance from the spacecraft to Earth's horizon rounded to the nearest mile? So that's basically saying what was the distance from the spacecraft to the edge of where they could see, right? So a good idea for anything like this is to draw a picture. And it looks like I'll have a lot of room over here, so I'll go ahead and do that. So I'll start with my Earth. And something you'll need to know for this problem is the radius of the Earth. And so we can look that up with our handy-dandy Google machines. And we'll find that the radius of the Earth is 3,959 miles, approximately. So 3,959 miles equals radius. And then from there, we know that 120 miles further is Apollo 11. I don't know why I drew a satellite, but there's my Apollo 11. So we're wondering what the distance is from this thing, right, to the horizon. So wherever, the Earth goes beyond our line of sight. And so to find that, we would have to draw these lines here. Find that tangent line, right? Because we want to find that point, that one single point where we can't go or where we can't see past. So that would be represented by one of these tangent lines. They would give you the same result, but we're just going to go with the top one because I think it's better drawn. And so we'll draw a radius from there. And what we can deduce about these things is that this is a right angle because these are perpendicular lines, right? If the tangent line and the radius are perpendicular, then we can say that that is a right angle and we can use that to our advantage. So now we know that we have a triangle here. I'll try and redraw it. So here's our right angle, here's our spaceship, here's our center. So we know that this length is 3,959. We know that this length is 3,959 plus 120. And we're trying to find this angle, or this measurement here. And so look at that. We've drawn up, based on this situation, we've drawn up a problem that we can address with things that we already know. As you can probably guess, the way that we're going to solve this problem of finding the legs of a right triangle is with the Pythagorean theorem. So we know that, first of all, we'll do this. 3,959 plus 120 is equal to, 4,060 or 4,080. 4079, I think. Yeah, okay. Sorry for that dramatic pause. Okay, so now what we can do is say that this number squared times this number squared equals 4079 squared. So we've got x squared plus 3959 squared equals 4079 squared. So really we have 4079 squared minus 3959 squared is equal to x squared. And so we really have x equals this. And if we plug that into our calculator, we will find that x is equal to 982 miles. So there's my answer there, 982 miles. Like I said, it was all in the setting it up to where we could use something we already know to find the answer. So go ahead and try example 4 on your own, and that is where we'll stop for this module.